Welcome back, everyone. So it's a pleasure to have Professor Shakuntala Baichoo here. She's a associate professor in Mauritius and also visiting scientist at Dana-Farber Cancer Center in Harvard. She's basically a cancer biologist and bioinformatician and an expert in machine learning and algorithms, big data. She works on, I believe, public health and so on, African bioinformatics initiative, all variety of things. So she'll tell you about some of them now.
Thank you. Thank you, Rahul. Some corrections. I'm not a cancer biologist. I'm a computer scientist by training. So 10 years back, I started working, getting into the area of bioinformatics. And currently I work with cancer, people who are in the area of cancer. And I'm gradually learning to be, I'm not a domain expert. I'm a computer person. And I'm still learning. There's so much. I think you know that machine learning is so broad. You keep learning every day. Okay. So Rahul always say I'm from Mauritius, and I realize that when I go somewhere, I have to show where Mauritius is, because many people don't realize where Mauritius is. So if you don't know where Mauritius is, it's in the African region, and it's next to Madagascar. It's a very small island, and very exotic tourist, so very famous tourist destination. Okay. So that's just to give you an idea where I come from. Okay. So this session from 2 to 3:30 is hands-on ML. So I sent 2 notebooks yesterday, which I've shared in Google Colab. And I think a few days back, I also shared a cheat sheet on Python using Python for data science. And if you think so, that because you won't be able to remember everything, however good you're in programming, a lot of the things you'll have to refer to it. So it's good to have the cheat sheet. Okay. And what I'm going to show you in terms of this coding today is just a very minimal of machine learning. Once you start doing it, you'll realize there's so much, and it depends on which area you're working, what kind of data you have. You're going to actually use the algorithm that suits your application best. Okay. So we have created 2 notebooks. One for classification and one for regression. Yesterday, Professor Saurabh actually explained what's machine learning, and what's classification, what's regression. So classification is you're trying to predict, a class. Now, the example I've given you in the notebook, it's a binary class. It's just benign and malignant cancers. But the exercise I've given to you consists of multiple classes. Okay, so that you'll have to work, and you'll have to find search things. I'll give you the solution later on, but you'll have to try. Okay? And regression, you try to predict a quantity. Okay? So you don't use, both supervised learning, you're not going to use the same algorithm for both of them. And then in both of them, I've done a little bit of preprocessing. I haven't done the same thing in each of them, but just to show you what are the different steps. So the whole machine learning, workflow that you have, it starts with you have your data, you have to do some cleaning, you have to do some preprocessing, and then you try some model, you test it, and then you see that doesn't work, you go back, you might have to preprocess your data again. It's kind of goes on like this unless you're happy with the model that you have. Okay? So basically, some of the basic steps of the machine learning. So this is what I'll do. The first one is classification. The second one is a regression. So I'll walk through with you, and you can try it. So these are on the Google Colab. Now, Google Colab, the interesting thing is that you already have, once you work in that, many of the Python libraries are already loaded. But a few of them you'll have to load, which I've put in there in the, like, for example, there's something called Lazy Predict. You'll have to actually install it yourself. So let's start with the first one. So which is, I'll start with the classification one, breast cancer classification. Okay, so I hope I can see, you have it in front of you. So if you can't see well on the screen, at least you can see that. So the data that I'm using here, it's actually, it comes from Kaggle. Okay, we are supposed to develop a machine learning model to predict breast cancer using the breast cancer Wisconsin diagnostic data set. Okay, you have a number of samples there. And now this data set consists of a number of features. These features are already computed from a digitized image. So you've seen that in the earlier session, they were doing machine learning with images. So basically, when you have images, you have to convert that image into a structured data form, because the image is not structured. You'll have to extract the features, create your structured format. So this one is already converted for you. It's a very clean data set. So you already have, a number of features that have been retained in that after doing the preprocessing. So the features have been computed, like I told you, from the images, from breast mass. They describe characteristics of the cell nuclei present in the image, described in this paper. So if you want to go and read more about it, it's an old paper. This database is also found on the UCI machine learning repository. I put the link there, you can get it from there. The different attributes that you have the ID number, the diagnosis. This is the outcome, it's a classification. So there are only two outcomes possible, malignant and benign. Okay, and then the rest of them, you have a number of numerical values. So I don't know if this, so you have the radius, you have the texture, you have the perimeter, you have the area, you have the smoothness, compactness, concavity, concave points, symmetry, fractal dimension, the mean, standard error, and worst or largest, a number of values you have there of these features, which were computed on each image, resulting into 30 features for the three of them. So for instance, field 3 is mean radius, field 13 is radius SC, and field 23 is worst radius. So they are for different things they've calculated that. We're only going to go into the detail of breast cancer right now. We're just looking at it from the data point of view. All the feature values are recorded with 4 significant digits. So it's a clean data set prepared. There's no missing data in this one, but the exercise I've given you afterwards contains missing data. So you'll have to go and remove the missing data from that one. Okay. So anyway, because I've already run it, so I put all my import initially at the beginning. But that's not necessary. Actually, when you're writing the code, when you need the library, you can import it at that point. Okay. So I've just put it here, everything together, but that's not necessary. The first thing, of course, you'll need is your pandas that you have to import, because you're going to read that table. Now, I sent you 3 data sets. One was a breast cancer, one was a body fat, and the other one is a TCGA data that's for the exercise. And I ask you to actually load that data in your drive. So when you're going to create Google, going to start with Google Colab using your Gmail address, it is going to create, a folder in your drive. It's called Colab, okay? So in there, I ask you to create a folder called data. So normally I like to, store my data in one folder and then my notebooks in another folder. So if you have your data in that, folder, then the code, the way it is going to work. Okay. But actually, to run this notebook, you'll have to first, mount that drive. Okay. So there's the code to mount the drive also there. If you go further down, I've written the load the data and explore. So this is the code, I've commented it, but the first time you're running it, you'll have to actually, uncomment this. Okay, you have to import the library to actually, mount a drive. So you'll have to run this. Okay, so that will help you to actually mount the drive. And once you've mounted the drive, and if you've stored the data in the folder I told you, so everybody will have this Colab notebooks folder created in your drive using the email address that you're actually using. And in there, ask you to create a folder, subfolder called data, and you just save it there. So if you have that, if you've already done that, then that should be able to, you should be able to work with that. So how many of you have already loaded this data set in your drive? All of you? Okay, the rest you haven't done it. So let me show you how to do that. So to do that, you have to go to your drive. Okay, so you go to your drive, you see my ColabNet notebooks. I'll have something like this. Once you go to Google Colab, you go on the fresh screen, you tap Google Colab, you click on that, you'll go there, it'll ask you which email address you want to use. So normally what I do as, as a recommendation, I never use my normal email address as Google Colab because, it accesses everything in there. So I always keep one email address separate to do these things using Google Colab. Okay, I don't use my regular, otherwise, you never know how, because it's everything that's free, security you have to be aware of. So just use an email address. Security. So that will be I have a number of, I was testing the notebooks, so I have a number of notebooks there. And so this is the folder it's going to create. For the time being, the notebooks that I sent you, if you click on that, it will open in my space, but it's only view, you cannot edit it. So you can say make a copy. You say file, say make a copy. If you go to the option file, you'll have that make a copy. And it says, do you want to save it in your drive? Then you will save it in your drive. And in your drive, you'll be having those 2 notebooks I sent you. Like this, the first one was, I think, breast cancer prediction, classification, version 1. And the second one was body fat prediction, regression, version 1 full. So you should be having this. So those who haven't yet done that, so the moment you open that, you say save that, those notebooks, you should be having a folder like this. And in there, you create a folder called data. So when you create a folder called data here, then you are going to go to data, and then there you will say, just load it normally like anything, file upload, and you load it there. You'll have these there. So I give you 5 minutes, and I expect in those 5 minutes, everybody have the data in that folder. And if you have any issue, just raise your hand, I'll come and see. There's the hands-on, so I'll just. Just click on that. No, I sent a second email. So yesterday when I sent those link to the Google Colab notebooks, the first time it wasn't shared. So then I think Gayatri re-forwarded my email where there were 2 links. Those were shared. So you should be able to click on those 2. So have you got it? Great. So you can rename it. Don't call it copy because you save it copies. It has a name copy. You can just save it. So normally when you're going to say make a copy, it's going to call it copy something. You can rename it. Okay. Yeah. Yeah. Okay. Yeah. Then you can go. What does it say? Okay, you have to save it in your drive. Create the folder. Otherwise, you can save it in any other folder, but then you have to change the code in the notebook to specify the folder. But it should be in your. I mean, you can load it from your, local computer, but it's better to have it in the drive. Are you all okay? Who else having problem? Good. Anybody else? Are you all okay? Sure. Okay. Because if you have any problem, it's better to fix it now so that you can do the rest. Okay, that's it. Yeah. So you. No, but did you click on the link I sent you? Did you make a copy? You go there? Yeah. So say file. Save a copy in drive. You go to your drive. Then you go to that and you see it in your drive. So when you open the notebook that I shared with you, go to file, say save a copy in drive. So it will save in your drive. Good. Are you all okay? Can I move to the next step? Are you all ready to move to the next step? Everybody has it in the drive. You have the data in your drive in the folder data. Good, great. All right, so you have everything. You can just, this should be okay. The libraries, just click on that, should work. So we can first run the library. I mean, just load the libraries. Right. So once done, you'll see there's a tick here. It's done. Then we'll mount the drive. So this code will be the same for everybody because you're working in your space. The content drive is for you. Everybody has that in their own space. So you can run that one. So when you say when you run that, it will ask you, permit this notebook to access your Google Drive files. This notebook is requesting access to your drive. Granting access to this will permit code executed. So all these things, you have to say yes, connect to Drive. And then again, here you have to choose the email that you're using. Choose your email, and then you go down, and there'll be a few things that you say you agree with too. And you say allow. Everybody's been able to load the drive? Yes? Good. At the back? Good. The next, you go and open the data set. That's very fast. And then whenever you're doing machine learning, it's good to always explore the data. I mean, to see, somebody also mentioned yesterday that you need to see your data, what it consists of, what's there. That's called, exploration. So do some exploration, look at the data. So first of all, I normally want to see what are the type of data I have in there. So df.info, that's the data frame, the info, and it will give you all the variables you have in there. Now you see that there is the ID, and very often when you have the data, you would have an ID in the data, and the ID that doesn't contribute to anything towards the outcome. So what I do normally is many people drop it, I just set my index on that. Because many times later on when you've got the results, the predictions, you might want to link your results to some variables in the original data set, then it's always easy to do it using the index. So I normally, further down, you'll see I've actually set it as an index. Now, the other thing it's important to note is whether you have any null in your data. So you can actually run this. This is data that's already been prepared. So you run that, and you'll see there's no missing data. All of them contain, there's no missing data in any of the columns. Null, yeah. If it's blank, yeah, it's going to read it as NA. So then that will give you, like, if let's say 100 rows, it'll give you 100 NAs. So when you look at it now, of course, when you have missing data, what can you do with the missing data? Actually, if you have some, it depends on you and the different, rules people use. So for example, if I have more than 10%, missing data in a column, I would maybe for some people more than 20%, you can drop that column, because how much are you going to impute? Especially in the space of health, you have to be very careful when you're imputing data. Okay, and for the outcome, if you have missing, you have to drop the rules. Don't impute, never impute the outcome, the target that you're predicting, never impute that. You can impute the features, the other variables, that also depending if it's more than 20% you drop, okay? Or more than 15%, more than 10%, it depends, on the rules that you're going to use. And so many, you can use like median, you can use mean, there are different, algorithms to use to actually impute that, you can impute that. And for categorical also you can impute, you have the, when you read through, you import the, the library for the imputation, you can actually maybe impute with the most common one, something like that. So this one for the timing doesn't have any missing data. And you can also describe. So when you describe, it's going to give you, the standard deviation, especially for the, this is for the numeric ones. It'll give you the standard deviation, mean, median, the quantile, everything it's going to give you. So that will give an idea, how is your data? For example, the variance and everything in the data, how does it look like? Then I know that the column, the target column or the outcome in this data set is diagnosis. So I'm going to see, I want to know how many classes I have in my outcome. So to see how many outcomes I have, I'm just going to look at that, the DF diagnosis, and I'm going to run that. So that will give me the M and B, there are two of them. And the other thing, I want to actually, visualize and see the distribution of the benign and the malignant. And it's very right to say that in health data set, the data are not balanced always. Many cases you'll get unbalanced data set. But this one is not that unbalanced. You have about 200 and something for the malignant ones, and about 350 and above, you have benign ones. So this is how my data is distributed between those two, different classes. So like I told you, what I do is I'll always, if I have an ID, patient ID, sample ID, whatever, what I do is I just set it as an index in my data set. Instead of having just a random index, I just set that as an index. So, and then I'm just trying to view the first 5 rows, and you can see IDs become the index. And now you want to know how many rows and columns you have. So the next one, you have row and columns. So you get the shape that will give you how many rows and columns you have. So there are 569 rows and 31 columns. Now separating the independent and the dependent variable as X and Y. So I'm not doing any feature selection in this one, but in the next one, in the regression one, we have some codes of features, choosing the best features. So in this one, I'm just actually, trying to use whatever I have in terms of features to try to predict the outcome. So what I'll do is I'm dividing my data set into the X, the features, and Y, which is the outcome. So the next code is just doing that. But before that, you know that when you're doing machine learning, the data cannot be categorical. So all the other columns are numeric except for this one. So what I'm doing is I'm doing a label encoder. I'm encoding one as 0 and the other one as 1. So these first 2 lines of code, 2-3 lines of code, I'm just encoding it. You can also do one-hot encoding. And there are different kinds of encoding you can do. But I'm just using the simplest one for the time being, it's the label encoder. And here I'm just trying to see what's there in my Y. You can also see what's, you see there's 1 or 0, it's encoded. The next is prepare your training and testing this data set. I don't have a discovery data set and another set of data from somewhere, but in this data sets only, I'm going to create one that's training and one part that's testing. So I'm going to use a train test split function that we have in sklearn, or I'm using scikit-learn. Okay, I forgot to tell you there are different libraries you can use in Python. So I'm using sklearn. So scikit-learn. So I'm using that, and you'll see that in here. I'm saying that I'm using 20% for testing. So 0.2, which is 20%. And then this actually it uses a random variable. So sometimes when you're actually trying to tune your model, sometimes you have to also tune this random number in your data set, your train test split. So you have just using one random number, you can use anything. If you just leave it, why do we do that? Because if you leave it, I'm not going to put that value. What's going to do that every time I run it, I might end up with a different result because it could just split it anywhere. Okay. And by default, there's something called shuffle, which is set true. Okay. So you ensure that the data is shuffled. Okay, so that you have some benign and some malignant that goes into the training and some that goes into the testing. And then the next thing that this is a basic, if you're doing machine learning, you do is you scale your data, because what happens is that many times when you're dealing with data set, you may have some, of the variables which are in the range of 1 to 10,000, some are in the range of 10 to 20, some are in the range of 100 to 200. Okay, so it's good to bring everything in the same, standard. So what you do is you scale that. Okay, so I'm going to use a standard scaler. There are different versions. You have min-max scaler. You have other scalars you can use. So we are just using the standard scaler, and it's been imported up there already. So what we do is we create an object of type standard scaler. Then I'm going to fit it on my X-train. I'm just going to transform, both the testing and the training. Okay, so fit it and train. Then I want to see, when I'm going to next see how does this look like after I've, sorry, I didn't run it, so I have to run it. Then you want to build your model. So if you're needing a classification, many times you don't need very sophisticated algorithms. So we start with the simplest one first, which is a logistic regression. Okay, the name is regression, but we use it for classification. So we're going to start with a logistic regression, and I've imported that already. At the top, you'll see. So So logistic regression is already imported here. So already imported. So we create an object of that logistic regression, and then we are going to fit that. So the result will be a model. We fit it on a X train and Y train. That is the labels we are providing as Y train and the variables for X train. So you know what machine learning is, just create a model. It's going to learn from that data set and create a model. Then I'm going to predict it on the test data set. So you predict on the test data set and you want to actually see the classification report. You have to, you just run the classification report and it's going to give you this. So yesterday in the class, we had, I think they explained about the precision, recall, etc., accuracy. So what is precision? And recall? Correct, yeah. And recall? You can check it, search and just check it. So these are the different, metrics that you can use to actually evaluate your model, okay? But I actually like to do it visually using the AUC, ROC AUC score. So there are many metrics available. This is one of them. And you also have the, the two-dimensional array that you use to actually show how many true positive, true negative you have, and then, false positive, false negative, etc. So this is one of the reports that you can have a look at it. But I normally like to see it visually how it looks like. So when I run this one, so what I've done in this case, now in the previous one, I just showed the prediction based on the test data. But actually what I like to always compare how my algorithm is performing in the training and the testing also. Now, of course, you tell me why training, because you train on that. Because some algorithms, when you do the prediction of the training data, which is already seen, it might give you 100%. But when you actually give it to an unseen data, it might give you 60%. So this is called overfitting. So if you have an algorithm that's giving so much difference between training and testing, this means that's not a good algorithm. So when you're going to run that model with unseen data, it's not going to give you good results. Okay, so that's why I'll always like to actually see the performance on the seen data and on the unseen data proof. So they are closer there, the better your algorithm. So if I have one algorithm that's giving, let's say on testing 80%, on training 99%, and I have another one that's giving, let's say 75% on or 76% on testing and 80% on training, maybe I'll go for the second one, because I know that the difference between these two is not that much. So when I give an unseen data, I know the model is going to perform as good as it's on the training data. Okay. So it's good to always see both of them. So that's why I'm plotting both the training and testing here. So you can see they're very much similar. So in fact, it's the same value. It's just a minor, maybe 2 decimal places. So you can see the orange one is for the testing and the blue one is for training. So they're very similar. Okay. So this means it's doing quite well. And of course, like I told you, it's a very good data set. All the classes in machine learning use this data set to show, how to use machine learning. Okay, then the next code that I've done is to actually, I've shown the, if I run this, I've actually tried one with the random forest classifier. So that one was logistic regression. This one is random forest classifier. I'm not going to go into the detail of random forest. That's the core algorithm thing, but I'm just showing you, you can try another one. And you do the same thing, the prediction. Right. And then you plot that. And you see in this case, like I told you, some algorithms might give 100% of the training, but especially algorithms which are like random forest, many times they do overfitting. So this one is still not that bad because there's 99% for the testing and 100% for the training. But in many cases, you might end up with one model whereby it's giving 100% on the training and 65% on the testing. And random forest is one. That's why I specifically chose that. It does a lot of overfitting. So you have to be very careful when you're using random forest. Okay. So then what I did is, I've shown the training and testing. Now what I did is, especially when you're trying a number of algorithms, it's good to actually plot, the AUC curve for all of them on the same plot, and you can see better. So what I've done, the next one is I've actually done the testing for all. I think I've used 3 algorithms. So you have the logistic, the random, and I've also done gradient boosting classifier. And then I've done the testing result for each of them, and I've plotted that. So here you can see all 3 of them is for testing, performance, for logistic, for random, for rest, and for gradient boosting. So they're all pretty much close. But then, we tried 3 algorithms. So we're actually doing, machine learning. How do you know which one to choose? I've just chosen 3. There are, plenty of them. So recently, you have a library that's called Lazy Predict, which is coming to, the space of machine learning, which actually doesn't do the, it's going to like do a very good work at, creating the models, but it will give you an idea of the different algorithms, how they're going to perform with your data set. Okay, so you have to first install the Lazy Predict library, and that doesn't come in the Google Colab. So first you need to install that, and you know that when you're in a notebook to install anything, because it's a command line. So for those who work in the Linux space, if you want to install something, a Python library, you can install using pip install Lazy Predict. But if you want to run command lines in the notebook, you just put an exclamation mark and it's running, installing there. But of course, this is Google Colab. Every time you switch off, your VM that you're using will be switching off. Every time you're going to run it, you'll have to do that. So you have to install that. So you have to install Lazy Predict. First install this, and you'll see something's going to happen here. To install that. So once installed, then you can use it. So to use it, just import Lazy Predict. Okay, and then from Lazy Predict, that supervise import classifier, because you have the regressor also. Just import the classifier, and then you create your model Lazy Classifier. And this is the I'm using the default settings. And then you'll see in this case, I'm going to create I'm creating the model, and I'm also create the predictions, both of them doing at the same time. So I'm going to create the model, and I'm going to run it on the testing data. So that's why I'm providing both X-train, X-test, Y-train, Y-test. So it's going to create that and then, run it and then print the models. So once you run that, it'll take a bit of time. It's going to run a number of, algorithms. So 29 of them, the most common ones, and you can see the performance. What does it give you? It gives you the accuracy, the balance accuracy, raw KUC, F1 score, etc. Lastly, it also gives you the, there's one more. F1 score, okay. That's it. It's the time taken. The last one is the time taken. That's not very important. It's important is up to you. So as you can see, the top ones, you have a number of them. So Berdui, naive, bias. You have passive aggressive classifier, SVC, support vector classifier, perceptron, MLP, multi-layer perceptron, ADA boost classifier. And this is the ADA boost one. People you use that. Actually, it gives quite a good accuracy in many cases. Logistic regression. Then you have SGD classifier, extra tree classifier, a number of them. Okay, as you can see, it goes down, and as you go further down, you see these will change. For example, like dummy classifier. So some of them maybe you've never heard about it, but there are all these possibilities. So that will give you an idea which one to actually choose and go and implement it. And then you can do the comparison, because any paper you're writing, any work you're doing, they say you always have to have a number of algorithms, and then you show the performance. So that's will give an idea. So normally I've shown you at the end, but you should run it at the beginning. And that from there you can choose the algorithms. So that's the very basic machine learning, classification task. And this is just the 0.0001 of what machine learning. Okay? The tip of the iceberg. You have so much more to do, so that you learn yourself when you're going to do your, whatever task you're doing. So everybody has been able to run all this? Who hasn't been able to run something in this one? Oh yeah, you have to complete it. Okay, yeah, I had said you have to complete, so I've already done that. So yeah, you can go. I'm just going to. So this is the one. Just create a random for us. Yeah, I was supposed to give you as an exercise. I did it. So you have to create a model and then just create your object random forest classifier and then fit it on your training. So run that. I give you a few minutes, try this, and then you can just repeat the copy paste the previous code for the plots, etc. You don't have the data? So are you in collab? Just in collab, yeah, you have a lot of data. Yeah, so here, answer. Yeah. So which email you have used? This one. Yeah. This one also is the same thing. Yeah. Yeah. So what is it saying? No. Okay. It should be in the folder data. So did you create it? So new folder data. Okay. So now it's in the, oh yeah, two of them. You have breast cancer there. Okay, and you have another data.
Yeah, well, I
How
just
did
made
it-
it now.
So how did it create today the files in the same way? Just
So
move
yeah,
this
I
one to the
forgot
bin.
If you look at the date,
Actually, what you could do is I could also just use.
I'm not
Yeah, we can just try that. There's no such file directly. Did you save it as CSV? Is it CSV? Yes, yeah, that's the problem. Have you all been able to load your data set in your notebook? Yeah, it should be saved exactly the way it is. .csv. And the other thing, we don't remember everything. I mean, I still check in above things. When I need, I just go and Google and or go to the documentation of scikit-learn. You won't, we possibly can't remember all this. You just need to know what you have to do. So just create your model. Okay. And then you can predict. I've called this one RF model. The previous one is called model. The same. And here you do the same thing exactly. Copy paste, just replace model with RF. Whatever. Oh. Did you load the same data? Not the one I gave you. Let's try this. It doesn't have any missing values. No missing values, you see? See, no missing values. It's just visualizing. 169. What does it say? X contains NaN. Yeah. Did it drop? Did it drop? No. Anybody's getting NaN in your, I don't know. Because this is a clean data. You're not getting this error of NaN. I don't know. I mean, I'm not sure. I mean, this is not a normal error. Is it from? Oh, the one I sent by email. Take the one that I sent by email. The email, in the email, there are two attachments. Just save them. Maybe that one has some issue. You're having issue with the data. If you download it from UCI, then maybe just, I don't know, maybe something is missing there. Just use the table I sent because I've already, cleaned that. It's okay, Nikki? You're not working? Did you save the CSV? No, this is not CSV. This is a Google Sheet. You know what? Just save it again. Remove this. Move it to bin. There's the email. It's here. Okay, so just load it. New. File upload. Yeah. Yeah, just save us. Load all three of them at one go. Load all three of them at one. Don't click. Yeah, don't click. Just say Control Z. Should work. Right. Copy link. Yeah, I will check that. We should be able to. Anybody else having issue, not able to load the data from the drive? No. It doesn't look like a normal. Okay. Yeah, everybody's done this part now? And the next part is just to run 3 algorithms, make the predictions on those 3, and then, you know, run it, show it visually. So normally what you can do is you can keep this as a template when you're going to start writing those who don't do machine learning, and then build on that every time. Area under curve. Rock AUC, area under curve. AUC under curve. So the bigger the area, the better the the accuracy. And if it's just, instead of using an actual, machine learning model to predict, if the line is just straight like this, you could just use the mean. So for this part, just copy paste, and let's keep on adding that. So this part, I'm just setting the plotting area because I want everything to be in the same plot. Later on, I'll share this one also. Can I move to the next one? To the body fat? The regression one? Because I see I have only 30 minutes. Yeah. Because I'll share this with you afterwards. This is the full notebook. I'm going to share it with you after the class. So let's go to the regression one. Okay, let's just walk through. So this regression one, we are going to predict, this data set also I've downloaded from Kaggle. And we're going to predict the body fat based on some corporal measures, for example, the length of the neck, chest, etc., etc. So I've given the description. These I just copied from there. What are the different fields that you have in there? So you have density determined from underwater weighing, percent body fat. This is going to be my outcome. You have the age, the weight, the height, the neck circumference, chest circumference, abdomen, hip, thigh, knee, ankle, biceps, forearm, etc. So this one has a bit more of pre-processing. That's why I want to go through this one with you. So you have all the libraries. Some of them I'm going to load afterwards. These are the libraries that we have loaded, okay? And you do the same thing here also. Import these. If you have your libraries there already. And then load the data set, mount the drive for this notebook. So again, it will ask you connect to Google Drive, those same thing, which email address you're using, and allow. then load the data set. These are the columns that you have in the data set. Again, you want to see what are the different data types, so you can see all of them are numeric. We don't have any, string data set in this one. I'm going to check if there's an NA. Again, this one doesn't have any missing data prepared. Again, you want to see the different statistics. Same thing. How many columns and rows? So 252 rows, 15 columns. One of them is the is going to be the outcome. So I'm going to create, as you can see, I haven't, this one I think I haven't set the index to be there's no index. There's no ID, so I haven't set the index in this case. I'm going to create the X and Y here. The body fat is going to be the target, so I'm removing it from, DF and creating the X and the Y. Then we'll do some feature engineering. So there are various ways to remove outliers from the data set. So I've used the Z-score, okay, to use the Z-score. And I'm saying that, if the Z-score value is less than, with all the scores less than absolute value of 3, I'm only going to keep those, okay? So the rest I'm going to drop. So this is kind of trying to, pre-process the data or trying to get, a better data set, improve my data set. So you can see earlier there were 252 and now 10 of them have been dropped. Now my features, I'm going to do some feature selection here. So there are various ways to do feature selection. What I've done is I'm going to look, correlation between the variables. Okay, so I'm using, for example, I've already created my feature and my outcome. So X contains all the features. Now I'm going to see if there are some, correlation between features. And if that's the case, let's say I have two features which are highly correlated, I don't need to keep both of them. I can drop one of them. Okay, there's no point in keeping things that are correlated with each other. The other ways that you can do is you can also use variance. So let's say you have different columns, and in one column, there's no variance between the data. So this means it's not changing, it's the same thing, more it's the same value. So you can drop that column. You have many other ways to do that. Sometimes you can do recursive feature elimination. So the various ways you can do. So I'm just showing one of them, which is collinearity. Okay, so and visually you can see that. So when you look at it visually, you will see some of them are highly correlated. So what I'm doing is I'm going to drop all those that are more than 80% correlated. In fact, what I did, without removing any of them, I run the algorithms, and after removing those that were more than 80% correlated, and half of them, if they're too highly correlated, I remove one of them, it's the same performance. So basically, these features are not contributing to anything. So it's good you can remove. Sometimes they use more than 90%. In this one, I've used 80%. So you'll see some of them will be above 80, like 0.86 between these two features. So this one is abdomen, and this is weight. Okay, in fact, you'll see weight is quite correlated with thigh, with knee, with abdomen, with chest, etc. So basically, there's no point in keeping weight because sorry? Yes? I can't hear you. Can someone? Yeah. I'm just using the function that's available already in there, the statistics function.
Yeah, but in the code, it is written Z less than 3, then only it is included.
Hmm.
But if you consider absolute value of Z, then Z greater than -3 also have to be considered.
I've taken absolute.
Oh, yes, yes. Thank you. Yeah, understood. Yeah.
It's absolute value, yeah. So, otherwise, more than 10 would be going. A lot of them would be going. Yeah, anyway, so you can see many of them are above 80%. So what I've done is to actually remove the highly correlated features. You can actually use enough because it's a symmetrical grid. So you can use the upper or the lower triangle. So I've just used the upper one. So this is the code to actually, drop those that are above 80%. And actually, if you do that, you will see there are chest, abdomen, hip, thigh, and knee. So in fact, instead of dropping weight, I've dropped the others which are correlated with, because all these others were correlated with, highly correlated with weight. So I've kept weight and the others have gone. Yes.
Ma'am, here you have kept the weight because weight you think is more related to outcome variable, right?
Yeah,
You
actually,
have
I did
removed
it. I
all
did
other
it
three.
computationally. I did it computationally because if you look at the grid, you'll see weight is correlated with the number of features.
So if you remove just weight, then removal of only one this weight variable
Then 4 or 5 other features would be left there.
can be kept, because weight is only highly correlated with all these predictors,
Yeah,
variables,
yeah,
right?
yeah.
So have you kept weight just because weight is more can more
Actually,
explain body fat?
I tried removing weight and keeping the others, but it was giving more or less the same, accuracy. Okay, so actually, whenever you have a lot of data set, and you should always choose the minimal number of features that gives you the result. And right now, I'm just working with 30 or 15 features. But when you're working in genomics area, for example, you could be having 400,000 features, 300,000 features, 100,000 features. So you'll always try to remove, try to downsize it. And actually, when I remove it manually, I remove the weight. But this, I'm using the algorithm directly. So the algorithm is dropping the other 4. Instead of dropping weight, it's dropping the other 4, which are highly correlated with weight.
Okay.
So,
suppose you don't have these 5 variables.
Yeah.
Instead, just suppose you had only chest.
Yeah. Then you would have got chest.
Yeah. So I'm going beyond this this formulation where you have the number of the selection depends on the number of predictors. Is your selection depends on the whether the weight is more can explain more than the other variables, the variation in the response, that is the body fat.
Yes, then in that case, you have to do a correlation with all of the features to the target.
Yeah.
That's another way also.
Yeah, because all other are just circumference.
Yeah.
And weight can directly influence the outcome.
Yeah,
variable.
it's going to actually, anyway, somebody who's heavier will have, the others will automatically be based on that. Yeah.
Yeah, so weight maybe on more cost side.
Yeah, maybe, could be. So actually, this is like I told you, there are various ways to actually do feature selection. I've just chosen one. And the other one could be actually, instead of looking at the correlation between the features, you look at the correlation between each feature and the outcome. So then only keep those that are highly correlated with the outcome. Yeah. Yeah, then also you can remove. So you could have done that one first. Look at each feature correlating with the outcome. Drop those that are not very correlated with the outcome. Then come to this step. Look at the correlarity again. Then drop those that related with each other. So you can do that. You could do that one first, and then you come this one. So I've just kept one.
Follow-up question: Why 0.8? Because
no, I said many people use 0.9. Actually, I wanted to show you that we can drop some features because none of them have a 0.9. So I wanted to show that this algorithm I'm using afterwards, it works and it drops, those that are above 80%. Yeah. This for the sake of, demonstration. But again, when I kept those without dropping this also, when I run the algorithm, the same workflow, it didn't change the performance at all. So this means when I drop these 5, it doesn't make any difference.
Yeah. My other question, you are choosing Z-score. So means, are you assuming that all these variables are normally distributed or something like that?
Yeah, well, I've assumed that, but again, that's not true. Yeah. So I've assumed that they're normally distributed. Again, like this data set that's used extensively, in machine learning, it's been clean, a very clean data set. So that's why we can do that. But again, in real life, like I told you, the same thing doesn't work.
Yeah, because if you just compare all these methods, all the methods are giving just more than 90% R square, right? Most of the methods. So data is just like that. Whatever you try, you will get the best result. That's
this one, yes, but the next exercise, that's why I want to reach to the next exercise. There you'll have to do some work. Okay. Let me finish this one.
Thank you.
Yeah, this is the easier part. Okay, so we've done that, and then you go to the same thing, the same train and test data sets. You create a training and testing. You can see. So normally I use, this algorithm. I don't choose myself. Unless, it's something really in the domain. If I'm working in the genomics, I know, like, for example, there's some genes which are very important, for example, in this cancer. And if my computational algorithm is dropping that, then I'm going to think twice. But right now I'm not thinking in the domain. I'm just looking at the machine learning that I'm doing. Okay. But then later on, when I do the survival analysis part, I'm going to give an example whereby I've actually chosen some genes which I think are important in there. So right now I'm just doing the machine learning. I'm not actually going to the domain. So create your training and testing, data sets. And again, you do your scaling. Again, I'm telling you there are various methods for scaling. When you're doing that, actually, you'll find out, you'll try a few and you'll find out which one works best. Maybe standard scaler doesn't work best. I've just chosen one to show you. This is how you do that. You can replace it, the code exactly with the other scalars that you want to use. And we'll try with a linear regression, which is the simplest algorithm. And in many cases, especially in health, like I told you, you don't need to go into the sophisticated algorithms. Many times, very simple algorithms like lasso and all these work fine. You don't have to go and use those. So try with the simplest one first. So we create a regressor in the same manner. Now here, actually, when we're going to do we're going to predict the accuracy. Okay. So the accuracy is predicted using the regressor.score, whatever regressor I've created has a function called score, and that's going to give me the accuracy. So I'm going to predict on the testing data set, but actually I'm printing also both for training and testing. So you can see I'm predicting for the score when I'm trying my model on my test data. And I'm also, writing down the score when I run the same thing on my trained data, which is already seen. I just want to see how it performs. So you can see in this case, on the training, it's 99% and the testing is 91%. Okay. So there's a bit more difference compared to the classification algorithm that we did earlier, which was about the same in most cases. But here you can see the training, it's giving 99%, which is seen already, and the testing it hasn't seen, it's giving 90%. Okay, so then you can try other algorithms. And to visualize, you want to visualize the regression line. So you can, you want to see how it looks like. So you'll see a few outliers in there. But most of them are doing pretty well. And there are other, metrics that you use to actually evaluate. So you know that the famous R square and et cetera. So you have the mean absolute error, you have the, the mean squared error, you have the R2 square, et cetera. So these are things you can read more about it, but I've just shown you this, how you can actually calculate them. And again, here you can actually run, use the lazy predict in this case also, but here you're going to use a regressor version of the lazy predict to see which one works best. So you have to install in this one also. Otherwise, you won't be able to run it. Use that and it will give you an idea of how these algorithms, the various algorithms are going to perform. But remember that lazy predict results that you get, you can't use that as your final result. It doesn't do the tuning and everything. Okay, and I haven't also shown you how to do hyperparameter tuning. Once you know which algorithm does well, you have to go and do the tuning for that. So that's again, another 1 hour lecture for that. You have to just go and read about it, and you should be able to do that. There are codes that are already been written to do that. So you can see there are the different algorithms, how do they perform, okay, on testing. So then you can choose the best ones. So this is, like I told you, 0.0001% of machine learning that I've shown you. Very, very, very basic. It's a lot more to do that. And then I have a data set I've shared with you. And in that one, that's not a very clean data set. There are missing data. There are a number of categorical columns. So for the same data set, I've given you 2 exercises. One is the classification and one is a regression. And specifically for the classification, I gave you a multi-class classification, the tumor subtype. So that one you have to find out a bit how to actually show the, the accuracy and everything, how you're going to plot those, because you can't use the same algorithm exactly for the plotting the rock AUC, etc. start working on that. I'll share the notebooks afterwards, but this is something that you have to start working on. So load your data in the same manner, start with the classification. Adjusted R-square and R-square, I need to read myself. I'm not a very statistics person. I just use it, computationally. Anybody in statistics can give me, well, I don't have the exact answer, to be frank. So what's adjusted R-square and R-square? Do you have any idea? Okay. Bigger, yeah. Maybe smaller. Thank you. Yeah, I suppose yes, depending on the number of features. Yeah, I mean, is it that just, I don't know. Yeah. So then when you adjust it, it gives you the, overall. Yeah.
But R-square should be between -1 and +1, I think. But in this kernel reach, it is showing -4.95 at the end.
Which one?
At the end, last model, kernel reach. If you scroll down,
So this adjusted, so maybe it's doing very badly. Need to check. So this feature, the lazy predict, I just started using that as just an indication. I don't really use it extensively, but just to get an idea. Yes. Exactly. Exactly. So the next data set has a number of categorical ones. So have you, let's get started with there are only 13 minutes left. You won't be able to do much, but let's get started with that. 20 minutes. Okay, it's showing 13. Okay, then we have time. Let's start. At least do the classification, because the regression will be more or less the same. Only thing, you'll have to encode your categorical variables. Don't forget. Yes. Yeah, the last few ones. Yeah. I just saw. We have to check that. It should be 0 and 1, of course, when you look at that. Yeah. You know what? Actually, what I do when I'm doing that, I always look at the top 10 ones or top 5 ones. I never go further down. So I never noticed that actually. We also look at the RMSE many times, the root mean square error. Did you manage to do it? It worked.
Something.
I was thinking it must be something we did right. Or maybe or maybe the other one, it doesn't allow you to use it. No, in the Google Colab.
Yeah, this Google phone. Yeah.
So the next data set, when you're going to actually look at the missing values, you'll have to decide. Some of them you'll have to drop, some of them you'll have to impute. To get started on that one. There are 5 subtypes in the tumor. So the first part will be the same. Mount your drive. Load your data. Then an interesting thing will come after that. So the original data set contained about 50 or more columns. I've just kept a few. Okay, just it's a partial version of that. So you can see not all of them are not numeric. You have some which are not numeric. The patient ID is just an ID. I'm going to set it as an index, but then you also have disease specific survival status. You have race category. You have stage. So these are not numeric. You'll have to encode them. And the next thing I do is I'm just setting my index. Like I said, many people drops that column, but I don't like to drop it. I like to keep it because there are further downstream processing why you might need to link your predictions with your, so then this index is useful. Then you do your number of missing values and you'll see there are quite a bit of missing values in there. And first of all, you'll see in my subtab itself, there are 91 missing. So subtab is my outcome. I'm gonna have to drop the rows because I cannot impute the outcome. Then you have race category. I mean, race category also, I mean, can you impute the race category of somebody? I don't think so. You cannot say that, you know, in general, there are so many Caucasian, I mean, European and so many Africans, so on average, I'm going to impute you to that. Doesn't make sense. So I would normally drop the rows that don't, if I'm using race category as a variable, then I'm going to drop the rows. And again, from imputation also, you have to see how much are you going to impute based on the percentage of missing. You can actually show the percentage of, you know, missing data. And then you say, okay, above 20% missing, sorry, below 20% missing data, I'm going to impute, the rest I'm going to just drop. Because if you have 50% data missing, you can't go and impute that. This is the status of your original data set, so you can decide, you know. Actually, I've left the disease-specific survival status and the month, because what I'm going to show in the survival analysis later on, that you can use this data set to practice that. First thing, drop all the rows where subtab is null, is any. And look at the, because once you're going to drop that, maybe those belonging to the others, other missing ones also will go. And how to drop, you have it in the cheat sheet that I shared. You should be having. The first thing that you do is drop all the rows where subtype is null, because that's my target. I'm not going to compute that. And look at the missing values again. The race category. So like I said, race category also I'm not going to impute. I can't impute the race of somebody. And similarly, I think I'm going to drop the rows whereby the disease specific survival status also, because if somebody is not dead, I can't impute and say, or if somebody is, you know, is really dead and most of the people are still alive, I'm not going to impute it with alive. Better to just, you know, drop those. In here, you have to think like, you know, in real life, whether you can actually do that. In stage of the cancer also, I don't think I can impute that. I can't say that somebody that's missing, maybe it's stage 3 or stage 5 or stage 4. So I would drop that also. And similarly, there's disease-specific month. That would go anywhere when I remove the survival status, because this data are together, come together, these two. And the next thing I'll do is, so I'm going to just, you know, impute some of the numeric columns. So month is score, aneuploidy score, and fraction of genome altered. While the others, like I said, race category, disease-specific survival, status, stage, and disease-specific months, I'm going to drop them. I cannot impute that. Yeah. I'm using drop NA. So the other drop NA means, you know, when those that particular column where it's NA, drop those rows. So then after that, if it's showing now there are only 3 columns that have missing values. So just for the sake of showing how to impute, there are more sophisticated algorithms for imputing, but I'm just going to use the mean value. The simplest one, I'm just taking the mean in the column and just filling them. But there is an imputer class that you can use from SQL. And after I've replaced the missing values here with the mean value, and check now all the missing values. So again, here you can go and do that collinearity or the correlation between the features and the target to, you know, to retain the features that are important. So those are things that you have to do. But I just want to show you something here, which is different from the previous classification, because that one was a binary classification. This one is a multi-class classification. So those plots for the rock IUC is going to be different. This one. Then you can see the statistics of the table. Let's do that. Then you can see, you saw that some of the fields are categorical. I mean, they are not numeric. So we'll have to encode them. So for that, I want to see how many of them are numeric and how many of them are not, object. Object means not numeric. So you see stage, disease specific, survival status, race category, and subtype. These are all, of course, subtype is my outcome. So apart from that stage, this one and the race category, they are not numerical. So I'm going to actually encode them. I'm using the label encoder. For the time being, I'm not doing the subtype one. I'm just doing the those three. The stage, survival, and this one, because I want to make a plot to show the distribution. So I can't put 0, 1, 2, 3, 4 for the time being. So we encode the others. And then if you want to see, time is up. Okay, I'll just get the time. So then I'm going to, so there are C 1, 2, 3, 4, 5 subtypes, cancer subtypes. So I want to plot that, see the distribution. Okay, of course, normal is the normal. I could have removed that. I haven't removed it for the time being because this is not, it's a different one. You can keep it's a normal breast cancer, but then you have the other ones, basal, luminal A, B, HER2. Okay, so these are various subtypes. And then, so I started with about 1,084, 1,024, 1,084 samples, and I'm left with 875, and there are 14 columns. So now I'm going to actually have to encode my target also. So I'm going to create my XY. Then because, it's multi-class, and I want to use that, so some of the algorithms for the accuracy, they won't work with the same one won't work the way it is with this one because it's a multi-class. So I'm not going to just use a label encoder here. There's something called label binarize. Because multi-class, I have to use this one. So then I'm going to separate my X and Y. No, sorry, I made a mistake. I shouldn't be doing this. This one I'm not encoding. Should be like this because I have 5 categories. There are 5 subtypes. It should be created like this. So just binarize and then this. Then I'm going to create my training and test same way. If you want to scale, you can scale it. You can just out of habit, I'm doing this scaling. Then I'm going to build a model. So now because it's a multi-class classification, I have to use a special type of, version of the algorithms. So for example, one versus rest classifier. And I'm using the logistic regression. I think I deleted. I think I removed some code from my. There's something I missed. What's the code I had? Sorry for that. Put the binaries, where would something like I think I've missed something when I was testing this. Anyway, something went wrong. I'll correct it and I'll share it with you. Just something else I wanted to show you here is that the code for the plot is going to be slightly different here. We have 5 classes. So there's something, I don't know what, there's one line of code that I've missed up there. I just need to fix that. So then we have to do it between the classes. And when we do that, this is the kind of plot we'll get for the different classes. So it will give you the AUC by class. Earlier it was for the same, I mean, you have this malignant and benign, but it will be giving something like that. I missed a line of code somewhere. I'm just going to fix that and I'm going to share that. So for multi-class classification, your ROC AUC curve will look like this. So you have 5 classes, they'll be like this. 5 or 6, whatever you have, 0, 1, 2, 3, 4. And there's a micro average. So the average is for all the classes. So micro average is light blue here. Okay. And then you have for the different classes. As you can see, the prediction in this case, it works best for this class too. So we need to find which is, no, this one, class 0. There's something missing. I'll fix that and I'll share it with you. I don't know what I did. I must have done something. This is, I did for this one, and I also did it for the, I did one for SVC. And then you get, I'll share it with you. I need to fix one line of code somewhere. So I don't know what I've done. It's this one that's giving me the error. This one. This is the one. I know where my error is. This. Yeah. The error was this classification report. So the normal classification report doesn't work with that. That's what was giving the error. So normally we don't label encode here. We just use the binarize. This, I didn't need that. So when you do binarize, you'll see the Y shape. It becomes, it's not just one series. It's like you have classes, you have 5 classes. And then you do the same, everything again, same. So this is what it is, this one I was giving me the error. So you have to use one versus rest classifier. And then I wrap the logistic regression with that one. Then you run it. And you should see this. So this is for logistic regression. And you can do the same thing with the support vector classifier. And you can continue with the rest. So I'll share this one. The regression exercise for this one is very similar to the other one. But you need to do those cleaning, imputing some of the missing column values in the missing columns, all those things. It will be more or less the same. But in the other one, the target is I think it's the TMB I've given, tumor mutational burden. Yeah, so then for that one, you can't impute. You have to drop the rows that contain NAs in that one. Never impute the target data. You can't impute the target. The outcome never impute. So this I'll share with you. This is slightly it's more complex. So you'll see in this one for the target, I haven't used a label encoder. I have used something different here. This is called binaries. I've done a label binaries here. Because if I did the label encoder, it will be 870. It will just be a series of 875. While here you see it's actually creating 875 by 5. So there are 5 classes. That's why, because of that, I can actually plot like this for each of them. It's using for all the 5 classes, and it's also showing the micro average. So there are 5 classes. You will see 5 lines plus 1 extra line for the average. For all the classes. Yeah. Area. It's also taking the number of, the first one has more. I think the first one is the Menon, while this one, you see, they have more samples here. So that's why when you average it, you see the average is about approximately 0.983 because this is a bigger class, while the others are smaller classes. Yeah. So it's, I need to check that one also. I've just tried it here. I just wanted to show you that you always do, in many cases, we're only doing 2 binary class. But sometimes, I wanted to, you may come up with something where you have more than 1 class. So then how do you actually tackle that? When you binary, it's very easy. A lot of things work with the binary classification. But when it's multiple classes, then a lot of the things that work with that one doesn't work with this. So then you have to, tweak that. For this one, you have to try in more. I've just tried 2. I tried the logistic regression and the support vector classifier. This one I use support vector. I didn't use a random forest. Then you have to look at all of them. Yeah, maybe, yeah. Yeah. Yeah, maybe you're right, yeah. But this one is, yeah. Yeah. That's why I actually chose, that one I just tried to, as the first, I always try the first one as logistic regression. And for, yeah. No, I think so. This is actually, this is what it's doing. That's what's giving you the accuracy for each of them separately. Yeah. It's like a multinomial. It's doing like a multinomial. Yeah. Yeah, maybe you're right. Yeah. Actually, I also normally always work with binary classification. When I gave this yesterday, then I realized the multi-class classification. I said, okay, when it doesn't work, I mean, all the normal algorithms won't be working with this. Yes. Yeah, yeah. Too simplistic for that. Cleaning the data. Yeah. Yeah. But again, I've used the very simple things. Yeah. And I think those who are doing machine learning, machine learning is not as, even though it's hype, everybody talk about machine learning, it's not as simple as that. It might take you days to just get, keep working on that, then you get something that you're happy with. Yes.
So I think we have an online talk at 4. So in order not to keep the speaker waiting, let's break for coffee now and come back for sharp.
So I hope that you had a glimpse of how you can, those who haven't done machine learning, how you can get started with that. But this is the very, very basic. Huh? Yeah, the smallest bit of the tip of the iceberg. Yeah, I'll share this one also. So these are like you have the template and you can now actually, yeah. Could you switch this off?